is our topic, 8 acids and bases. And last time we spoke about the definition that came from Arrhenius, who at the turn of the 20th century, and somewhere around 1903, he got a Nobel Prize for his work in defining what is an acid and what is a base. Okay, so he defined acid as something that can ionize in water to produce protons or hydrogen ions. And he defined an alkali as a soluble base that produces hydroxide ions. And he said that when these two things combine, you can call it neutralization. Now all of that is correct. That is entirely correct, that bases produce this, acid produce that. And when they come together, you have neutralization. For example, like this. Acid, hydrochloric acid, base, aluminum hydroxide, you get aluminum chloride, you get water. But this was a limited definition because it could not account for something like this. When you have ammonia, which is behaving as a weak base, reacting with hydrochloric acid to give you ammonium chloride. When you have that, that did not fit into this definition. See, this definition is only confined to what? A base being what? Something that supplies this.
I know.
Whereas this here now is behaving as a base, but it's not associated with this. So there was the need to redefine or to move from one belief system into another one. This is something that happens, that has happened in the history of science very often. It's a paradigm shift. As one thing that was quite groundbreaking and quite well respected enough for Arrhenius to get the Nobel Prize. But then later on we realized that it's not all inclusive, so it needs to be refined, it needs to be reviewed or revised or whatever you want to call it. So there was a paradigm shift, and we expanded this to have what is known now as the Bronsted-Lowry theory, and they defined an acid now as something that can donate or give a proton or a hydrogen ion. So an acid is a proton donor, base, proton acceptor. With this definition, they were able to cover something like this. Because what's happening to ammonia here as it's reacting with hydrochloric acid? What is it doing? Is it donating or is it accepting a proton? It's accepting. It's becoming NH4Cl, and this is giving up a proton. So you have a Bronsted-Lowry acid and a Bronsted-Lowry base. So this is the definition of an acid and a base. Then we went on from this to speak about the conjugate acid and base. So here you have H2SO3 plus water giving you HSO3 negative and the hydronium ion H3O plus. What's happening here with this as it becomes this? What is it doing in terms of this definition? What is it doing?
A proton donor.
It's behaving as a proton donor. So it's behaving as an acid to form this thing here. This, on the other hand, is doing what? It's behaving as what?
Proton acceptor.
It's accepting a proton and it's forming this. If we look at this in the reverse now, if this has to go back to this, what is this behaving as?
Proton donor.
As you're donating this proton, and going back to this, and this would have to be accepting the proton and going back to that. So it's each one is the reverse of the other. And this pair is referred to as the conjugate pair. And how is this pair, how is this member of the pair different from this member of the pair? There's one single thing that's different. What's different between this and this?
That's an ion. I mean, that's a radical proton.
The missing proton. A proton is lost as you go from the conjugate acid to the conjugate base. And a proton is gained as you go from the base to the next one. Because an acid is a proton donor and the base is a proton acceptor. So sometimes we have structures that can behave as both a Bronsted-Lowry acid and a bronze glory base. One such structure, it's well known, is an amino acid. So here we have a simple amino acid. This is the simplest of the amino acids. This amino acid is known as glycine. This amino acid is capable of receiving a proton times, we go in there, or it's also capable of donating a proton from here. So it's got the properties of Bronsted glory. What on this side? Base, because it accepts a proton. And here it's going to behave as a Bronsted glory because it's going to donate a proton. In the same structure, yes. In the same molecule. Okay? It has this capacity to accept a proton or to donate a proton. When you have such a structure, it is referred to as an amphiprotic structure. Now the question that we took up last time is something that is amphiprotic also amphoteric? Now we need to look at the definition of what is amphoteric. An amphiprotic substance is one that can behave as a Bronsted glory acid or a Bronsted glory base. For example, something that's amphiprotic is what? For example, what? Amino acid. It can receive a proton or it can donate a proton. And we've also learned that an amphoteric substance is one that behaves both as an acid or as a base. But behaving either as an acid or a base does not necessarily mean that it's behaving as a proton donor or a proton acceptor. Something that can do both of those, either donate a proton or accept a proton. What do you call that? Amphiprotic. Something that behaves both as an acid or a base. So it means, if you think about it, once something is amphiprotic, isn't it behaving as an acid and a base? Proton donor or proton acceptor. So all amphiprotic substances are amphoteric. But if something is amphoteric, it could be behaving as an acid or a base that's not a Bronsted glory acid or a base, because acids and bases can be defined in different ways. See, beyond Bronsted and glory, now not going back to Arrhenius, but beyond Bronsted and glory, now further expansion, further development of this idea came from Lewis. And Lewis defined an acid as an electron pair acceptor. Not something that accepts a proton, that accepts an electron pair. And a base as an electron pair donor. So sometimes things can have acid and base properties, but it's coming from the fact that they're donating electron pairs or accepting electron pairs, which in this case won't be protons. So they won't be amphiprotic, because this only applies to whether a proton is accepted or donated. But they would still be amphoteric, because they would have properties of maybe of Lewis acids and bases. Now all this discussion here, what was done here is for each other. So it means that this whole thing that we're taking on about what's amphiprotic and what's amphoteric, it's really for HL only. So this piece here we will come back and talk about in the HL only day, but I want the HL people to take a look at it right now. So we will just get an image of it in your mind, so that you'll be coming back to talk about that during HL. This is showing you some examples of how things can be acids and bases. Things can be acids and bases without donating protons or accepting protons. So, in other words, this one is confined to the Bronsted glory theory, which belongs to this definition. This definition can include other things. So, it's like all Indian citizens belong to planet Earth. But if you belong to planet Earth, it doesn't mean that you're Indian. It could be an Indian. So it's a situation like that. All amphiprotic substances are amphoteric, but not all amphoteric substances. This is what I want you to get in your head, which is why I want you to put down a discussion. Okay? To convince yourself, maybe not me, but you get this. Because this was a question that came up last time. We are now finished with topic 8.1. We're moving on to topic 8.2. Once we get done with the whole of 8.1 to 8.5,